Perfect. All right, great. So yeah, Rachel, the dean is still in a promotions meeting, she said, so it's running late, apparently, probably because they're giving out extra promotions like they always do. So you have to put up with me and my horrible accent for introductions as well, so apologies for that. So I'm Chris Lorenz. I'm the head of Department of Engineering, and it's my great honor to introduce our two speakers tonight. And before we even start, I'd like to thank everyone for coming and supporting my fantastic colleagues. So our first speaker today is Professor Harris Makatsoris. How do I say it, Harris? All right. I'm American. I can get away with it. Right? Harris is a professor of manufacturing, and he's the deputy head of Department for Research in our department. He is also the founder of Centillion Technology Limited, a UK biotech focused on rapid, scalable RNA therapeutic and vaccine manufacturing. He's had 28 years of experience in academia and industry, and through that, he's led interdisciplinary projects at the intersection of process engineering and bioprocessing. He is an expert in continuous manufacturing using flow technologies and has pioneered flow-based technologies for RNA and nucleic acid production. His research, supported by over 30 million pounds in funding, led to significant innovations in advanced medicines manufacturing, including the COVID vaccines, and he holds several patents and is highly experienced in industrial technology transfer and commercialization of bioprocessing innovations. So Harris, I'm sorry I butchered your surname, but I look forward to your talk.
No worries. Okay, let's hope I'm not going to electrocute myself with this thing. Right, okay, thanks very much everyone for coming. I will be moving around a bit. So let's see, I'll try to keep this to 25 minutes. That's a big challenge, I can guarantee that. So what this is about is a bit of a cross-section of the work that I have been doing for the last, 25, 30 years or so. And I thought I would share with you some of the stuff still has not been published, some others has been published, and I wanted to share it all today. So, when I was a kid, growing up in the 80s, I was just like many other kids, right? I was captivated and greatly inspired by these two fellas. So when I came here to study, during my undergrad years, I worked with Professor Brian Davis at Imperial College in developing this robotic knee surgery robot, which has actually, I don't want to take any credit, but actually this has been now in production. It is now in use. I was one of the early people got involved in this project. But of course, in the mid-90s, trouble was robotics was almost a bad word, so I had to think creatively. So I focused my efforts towards manufacturing, and to do that, I was starting to work across length and time scales. So increasingly, I was going down in length and time scales, exploring how to develop processes to make advanced materials faster, better, cheaper. So that started to be my thing. And during that early time of exploration, I started working together with the UK materials chemistry and the UK community and the UK organic chemistry community. And I established these two networks, very successful networks. They have both been running for 10 years, funded by IPSSE, exploring molecular self-assembly one, and this one was all about automating discovery in organic chemistry, organic synthesis. So that was a great inspiration because as soon as I started working with my colleagues there, I realized that there's a lot to be done, okay? There's a lot of manual workflows, even to this day. And what colleagues in this space are doing, they're trying to navigate the vast space of options by doing chemical reactions, trying to understand and develop new chemical reactions to discover and invent new materials, including primarily, what I'm mostly interested in, advanced pharmaceuticals. So if somebody considers the space that is available if you take all the various options, including, of course, processing. One can easily come up with big numbers like this. So just to put it into context, all the stars of the known universe, even beyond, are considerably less than this number. Okay? So this is the challenge of the problem. However, we still have to work fast, super fast. Now, this is a slide my friends and colleagues from CEPI normally show in their presentations, and actually shows a very gruesome reality. It shows if we had the ability at the time of the pandemic to deliver a vaccine within 100 days, and that's actually their mission, and CEPI is the Coalition of Epidemic Preparedness. They have been set up primarily to do this, so that's their mission, that's their religion. Then this could have saved millions of lives lost, trillions of dollars in economic damage. And just to put it in the context of the complexity of the problem, the SARS-CoV-2 spike protein, which is what vaccine developers actually targeted, its sequence has about 10 to the 600 permutations and combinations. That's a very big number. That's a real number. And all we had to do is pick the one that actually worked. Okay, it's good fun. And this is how it was kind of done. And looking at a lab 100 years ago is not too different to what we're doing literally today. And actually, even today, my lab looks more or less the same. It's a little bit tidier than this, but nevertheless. So I thought, okay, great. That's a very fertile space. And maybe this is the killer application for robotics, not the stuff I was looking at in the mid-90s. So I started theorizing and working on how a robot chemist or a discovery bot could actually look like. So what you need some way to encode the user input, some way to get the user prompt to trigger this loop that includes, in a closed loop manner, an actual physical system that creates the material you want, much like what people are doing on the bench, be able to evaluate and analyze, ideally automatically in the same loop, and then learn from it and iterate by establishing new conditions for the robot to run. Okay, this has not been done before. Okay, still, this is something that is outstanding. And of course, there is a question: why do all this? Okay, looking at it from a sort of philosophical perspective, why bother? And there is two key reasons why we should bother. First of all, is to confirm understanding, because frankly speaking, if we cannot make a machine to reproduce a phenomenon, do we really understand it? So this is number one. That's a very long-term goal, actually. It's a super long-term goal. And the other one, of course, point-blank increasing productivity. Okay, getting data, analyzing data, and doing all these wonderful things that we do with it. So we have seen AlphaFold by the DeepMind, now part of Google, earning a Nobel Prize last year in actually coming up with computer systems to help design, analyze proteins, help them design new proteins, and actually understand fundamentally how proteins fold, a very long-standing problem in the space, a decades-old problem. These people claim they have solved it. I mean, they've got a Nobel Prize for it. And actually that has started to bear fruit by allowing people to develop new drugs and new therapies. What we did some years ago, we had a different idea. So we developed algorithms starting from prompts that actually look like this. So chemical structures, these were known molecules. You can have two or more prompts. We created a very large space by an evolutionary algorithm iterating around possibilities to actually discover what other similar structures could exist in this space. And the theory was, if the structure is similar, that means potentially the actual function will be similar. So we came up with a generation of about 400 in this particular experiment. These were new molecules the algorithm discovered. And just for laughs, we went to the patent databases, and we actually saw that these were actually known chemical entities. We had, aspirin, paracetamol, painkillers. These were actually patented painkillers as well. That was really cool. Of course, that was not enough. As an engineer, okay, doing computations is absolutely awesome, and computation is running through my veins. But also, I like to build stuff. Okay, so how about we actually have a physical system to actually make these things, make some of these molecules, and explore how they can physically be synthesized. Because theorizing to actually making is a very long way away. Okay. So we came up with two key requirements. Number one, to be able to rapidly iterate, so we can put them in that computational loop to do the search of the product in a small scale. But also, we wanted to have the ability to take it to larger scales, market scales, without any complicated process development. How it's done right now, I mean, this is another, from lead discovery to actual manufacturing, is another 3-year project in the real world right now. So we wanted to accelerate this. So we wanted to have, a device, a machine that would allow you, once you discovered your product, to also have your process. So that was the sort of motto, mantra we were using. Come on. Okay, I think this has given up. So back to good old manual days. Okay, so first iteration, very ambitious. I thought, okay, let's develop a computer system that would allow somebody to actually design a sort of a molecular crystal, a material, and using some sort of a desktop device, borrowing ideas from atomic force microscopy and scanning tunneling microscopy, manipulate, smaller fragments of this particular material, small molecular units, assemble them bit by bit in a way that is completely inaccessible to traditional, organic synthetic chemical means, and then have the ability to scale up by numbering up with parallel operation, such that you generate a sufficient quantity, put it in a crystallizer. This is a very traditional, very typical route in pharmaceutical manufacturing, but in other areas of materials manufacturing, to create the bulk material, be it either a drug or even engineering materials as well. That was super cool. And we started doing simulations. Of course, we had to work with very advanced type simulators. We used quantum mechanical simulations. So we set up an experimental system, silicon surface, and we thought, okay, why don't we start by trying to play with the atoms on the surface? And we sort of created kind of like a molecular switch. This is the result of the simulation, the little video that I just played, and you could see the silicon dimers switching on and off. And an application of that could have been super high density storage. We also designed tools to manipulate various organic molecules on surfaces. And this is the energy landscape calculations we did. Of course, the question is, how do you actually do this, okay? For manipulating individual molecules and atoms and what have you, how do you actually do this? Well, let's see. Here is our crystallizer. How much of that you want to actually, as a seed, to actually create a bulk material? Those in the know, we think, okay, maybe 1 mole or fractions of a mole. Look at the exponent here. That's 23 zeros, okay, behind this number. It's a huge number, right? So it was like back to the drawing board. It was a cool piece of work, but then I wanted something real. So I started looking at, what other things we can do. Of course, conventional manufacturing is a technology, has been around for 150 years or so, very well known, very reliable, very difficult to manage. okay, and has very high risk in production, very expensive to run. So I thought, okay, maybe we should do better because I can demonstrate with a simple thought experiment. Everybody knows how to cook pasta, right? By the way, I have shamelessly copied these slides from somebody else, but I thought they were really cool and they actually demonstrate the point really well. Everybody knows how to do this at home, okay? You need about 20 minutes and you are done. Just put half a kilogram inside boiling water, wait for a little bit, and you are done. Okay, try to do this with a half a ton of pasta, industrial scale. It happens every day, right? If we were to use the same process, this is what we would need. Boil 3,000 liters of water, you need, I don't know, 6 hours. Decant the spaghetti, half a ton, inside tanks that could look like this. They actually look like this. You need about an hour for a 10-minute process time, cooking time, and then another 20 minutes to take off the water. So you end up with an inedible goop. I mean, it doesn't work. So people, again, had to go back to the drawing board just like I did. And they came up, actually, that's a real process. So what you have a continuous conveyor belt inside boiling water. You take the drying pasta, 10 minutes residence time you collect, and you can scale up by numbering up. Parallel operation. Job done. Can we do the same? And this is actually where what we started to look at, how we can develop flow reactors, flow technologies, just like the one we've seen before, but in this case, to make all these nice advanced materials that we wanted, promote self-assembly, the synthetic organic chemistry, satisfy those communities and actually invent new stuff. So the trick here was to actually make sure we manage the conditions inside the reactor to have a proper continuous flow process. And to do that, we designed new type of reactors, and these, of course, are all patented now. Okay, so let's see an example. So this was a really cool project with a Cronin group in the University of Glasgow. Lee Cronin is a friend of mine. He's an amazing scientist, and he comes up with all these crazy molecular structures. These are inorganic polyoxometal-led molecular clusters. And what is cool about this is if you change the process conditions, you actually come up with different products that have different process properties that you can actually measure. That was really cool because it allowed us, A, to be able to define the space of available options on the basis of physical properties, physical observables we can actually measure. And we used our expertise in evolutionary computation as well as some localized search algorithms, and combine those with physical hardware, actual physical hardware, okay, that can do reactions and they can do the measurements. So this is how my lab looked like 100 years ago. So you have all these tubes and bits and pieces, all driven by the algorithm. This is how the sampling and the measurement is done. You have the physical property in white, and then the algorithm converts the physical system towards the desired property, which was, this white spectrum picked up by a spectrometer. And you see how the system converges to the actual material that was targeted at. That's the set space. This is all you can make in this particular space, different molecular classes with different architectures, all very measurable. That gave us, this piece of work and collaboration gave us a nice paper in Nature Chemistry some years ago. Then we evolved the reactor system. This is now with a collaboration with the Bath University, where we're making, in this video, a very interesting switchable material, an advanced functional material. Now, the applications for this are not pharmaceutical by no means, but they are for engineering applications. That was another cool piece of work. And since then, we have been using this technology to look at various, we did a lot of work with these platforms for organic molecule discovery to gold nanoparticles. That's a collaboration with UCL. And this is actually now where Centillion comes in. We did large-scale bioprocessing, so we scaled up a cell culture to insane amounts. So through the work, we were able to show that you can have these platforms which you can automate. They're highly reproducible, highly scalable. You can reduce, manage risks, and have everybody happy, the developers, designers, as well as the process engineers. And all that led me to the RNA space, working together with Professor Robin Sadok, who's here in the audience. That's where we started to look at RNA vaccines and then evolved into therapeutics as well. So the process is very complicated, kind of looks like chemistry, but not quite, much more complex molecule. So it's a templated chemistry. So you start with a DNA template, and you have a biochemical process that involves enzymes that actually, using that template, create your RNA sequence. Then you take that and you encapsulate, you physically place those RNA molecules into another very complex structure comprising of a variety of lipids. So it's a lot of materials, right? And then how this works once injected in the body, this nanoparticle can penetrate through the cell's wall, delivers the payload, then the ribosome picks up the RNA once the nanoparticle cracks open, and it translates this into the protein that the cell expresses, and the protein could be an antigen, could be whatever target the designer has for the particular indication. So immediately, as soon as we started the project, I thought, okay, let's apply all these nice things we have been doing in the past and transfer them into flow. And actually, that was really cool because A, it worked. It was very serendipitous initially. It worked really well. We came up with a modular flow bioreactor to do a good subset of these processes on a microfluidic chip. And actually, we were quick enough to patent this right on time. So we have really good protection. That was really awesome work. We then taken forward. And what was crucial, actually, this approach was not only faster, better, cheaper, but also very well aligned with this type of chemistry, this type of system. Primarily because this control gives you the ability to control impurities, and impurities in this space is very important, very hard and expensive to control. And this is one of the biggest achievements. The other one, of course, is scalable and readily applicable into a regulated manufacturing facility. So all that was well and good, and then this happened, which actually led us winning an award, a very prestigious award by the Royal Academy of Engineering for our services against the pandemic, and attracted a lot of attention. The next thing that happened straight after was this call for proposals, a development project by Wellcome Leap, primarily funded by Wellcome, and our friends at CEPI I mentioned before. A very significant project, not a research project, but rather a development project. And our response was what we call the biofoundry in a box, everything underpinned by flow technologies, but develop an actual factory that is an automated, multi-purpose factory that can deliver a wide variety of RNA-based drug products, not just vaccines, but also other therapeutics. I put together really a world-class team to do that. Robin, you can see yourself in that. Plus a bunch of other colleagues, both from academia and industry, a lot of colleagues from King's. This has been taken actually in Guy's. And everybody actually had a very specific part in this project, and they all delivered because we had to. And we delivered really, really cool stuff. So what we did in King's, using now platforms donated or given to us by Centillion, our job here was to navigate and map this process space. And we did this by doing the reactions, but also doing a hell of a lot of analysis, okay, across a multitude of quality attributes, multitude of attributes of this product, measuring productivity, measuring purity. The smaller the bars, the better the purity, and this is us compared to conventional methods. And the peaks here, the sharper the peaks, the higher the purity, plus a bunch of other things. And we did a lot of experiments here in King's, a lot. We generated a lot of data that we then used together with our colleagues at Imperial Chem to actually map the space and try to understand the space with the view to develop a process digital twin. And give us the ability, given certain inputs, and this is the evolution of the model during the project, given certain inputs to predict performance and automate this process development process. Moving towards this red slide I showed earlier. Okay, so let's see how this can evolve. So this is a vision piece by Centillion. So how we can actually deploy this biofoundry in a box and secure equitable and rapid access to advanced vaccines for everyone everywhere. Let's see what the vision is. So imagine you can put all this technology, manufacturing technology, in a portable shipping container with a few additions. This has a clean room integrated, and ship this anywhere in the world. Okay, especially deployed in low and middle income countries, such that they can get access to advanced vaccines at less than $1 per dose. Okay, so let's see how this could work. Okay, so that's a vision. I mean, it does not exist at the moment, but I am sure the engineering design has been done. So another progression of this technology, this is, we've seen this is how bulk RNA vaccine product is made. We have seen these steps before. Let's see how it could look like for a personalized treatment like cancers and a bunch of other things like autoimmune diseases and stuff. So, the middle bit looks almost identical. What is different here is that you have the patient in the sort of chain where you take the biopsy, you use do analysis, bioinformatic the hell out of the samples to actually understand how to design, against a particular mutation or your antigen or whatever it is, the particular protein of interest. And that leads to the generation of the DNA template. The rest of the manufacturing process is the same. And then you have the patient at the other end. The biggest difference with this is that you normally, with these therapies, you tend to rinse and repeat, okay, to continue treating the patients for a long time, if not forever. The other piece of further work that I see is develop self-learning machines, so use reinforcement learning actually, and move forward all these algorithmic approaches that were at a very basic level so far, and integrate those machines and make them really intelligent so that they can do discovery on their own, work in parallel, do discovery on their own, and not just with those biomolecules, but with other things as well. And that's it. Big shout out to all my friends and family and colleagues. And that's that from me. Thank you very much.
Well, thank you for that really nice talk, Harris. I think, so in my group, we do simulations similar to what Harris did, but I'm really so impressed because Harris actually then builds stuff, which is, bad things happen when I go into chemical labs. I was a chemical engineer, but nothing like that. And Harris's, both of the people speaking today have had such a huge impact, not only on our department, because I think they're employees 2 and 3 or something like this of the relaunch of engineering, and so they have. I always joke with Claire and Barbara, and I should start joking with Harris that they should sign a brick somewhere in the quad because I think they laid the bricks themselves. So not only have they impacted the department and the amazing trajectory that it's on, but also Harris serves as a great mentor and supports a lot of our academics with their grant writing and et cetera. And also, obviously, his research has had massive impacts, which is always very impressive to me. Also, I just learned that he's friends with Lee Cronin, who I follow on X or Twitter or whatever it's called these days, and is like the most mad scientist I've ever met. So that makes a lot of sense to me. And I wrote something. Oh yeah, and I think also now I know if someone asks me, what does Harris do? I'm going to say that you have found the fountain of youth, because if that lab was 100 years ago, I mean, you're doing pretty good, Harris. But anyway, thank you for a great talk, Harris, and thanks for being a great colleague and a great support to me as head of department, and also for relaunching the department. So thanks again.
Thanks very much.
So now is when I would leave and Rachel would come, but I'm just back here. So the next speaker is Professor Claire Lucas. That's a surname that I can handle. Claire is a professor of engineering teaching and learning and the deputy head of education for our department. Sorry, the folder's in a bad place. Since 2020, she has led research and initiatives transforming engineering pedagogy and professional engineering skill development. She pioneered a create-first approach to engineering education, placing creativity at the heart of the engineering curriculum. Before joining King's, Professor Lucas was Director of Studies for General Biomedical and Systems Engineering at Warwick University, and previously led simulation capability improvement projects at Jaguar Land Rover. She is a Principal Fellow of the Advanced Higher Education. Professor Lucas was Deputy Chair of the 2022 QAA Subject Benchmark Statement and is an IET academic accreditor. She was recognized as one of the top 50 women in engineering in 2020 and received the Women's Engineering Society Prize at the IET's Young Woman Engineer of the Year Awards in 2019. And it's my great honor to introduce Claire Lucas, who's going to give our next inaugural lecture.
Thanks so much, and thank you everybody who's here. And for the people who aren't engineers here, it'll be a slightly lighter presentation than the amazing one we just saw from Harris. So yes, and thank you to everybody who's ever given an inaugural lecture, because I've now watched 20 of them on YouTube to figure out what it is you're supposed to talk about. So this is a bit of a narrative, a story, and of course it's 5 years since Harris and I joined, so it's also a bit of the what happens next, what happens once you get to have the dream job. So at this point, normally engineering inaugural lecturers would be showing pictures of themselves playing with Lego. They'd be like, you know, I was always going to be an engineer. If you caught me, I'd be in my room taking stuff apart. And that actually wasn't me. I'm going to tell you a different story. So I grew up in the very north of Cumbria, as far north as you can go in Cumbria. And our village was famous for two things. So it's the start of Hadrian's Wall. If you've ever walked Hadrian's Wall, you'll have started in our village. And also it's got, for all of the amazing telecoms people that are here, it's got this very low frequency transmitter, the NATO one. And it's also got some atomic clocks used for keeping time. But as a child at school, I learned a lot about the Romans, dressed up as the Romans, had lovely Roman meals, went to visit the Hadrian's Wall. We never learned a single thing about those masts. They, to me, were just the masts that were dominating the skyline of where I lived. And the thing which impacted me most growing up was that as a community, we were really devastated by foot and mouth. So if you're not from the UK, foot and mouth was a horrendous thing that happened when cows got ill, but it didn't matter. It was a bit like the precursor to COVID. It didn't matter if your cows were ill or not. All of the cows were killed within miles and miles radius the minute that any trace of the virus was found. And we were all locked down. We were the original lockdown of the UK. We couldn't go to school. We couldn't do our GCSEs. And this had a huge impact on our community and the trajectories of the people in it. And what I learned from that and what I took away from that is that my community did not matter to the people making decisions in government. So the people in London who were saying what was the right thing to do did not place any value on our community, which then had farmers committing suicide, and people losing their entire livelihoods and farms and incomes because of this. So that really drove me to want to become a lawyer. And my amazing lawyer friend is here. So what do you do when you want to be a lawyer? That's what clever girls want to do, right, at school. So I decided to do my A-levels in stuff I was good at and stuff that would help me be a good lawyer. So maths, further maths, English literature and history. Still liking the Romans with the history there. I was lucky enough to go to a law residential at Brasenose College. And I can tell you within 1 hour, I knew I did not want to be a lawyer. No shade, Joe. It was like the most boring thing I'd ever done in my whole life. So luckily, as Oxford often do, there was an engineering residential going on at the same time. So I managed to get into that engineering residential. Absolutely loved it. The rest is history, but not straightforward history. The obvious problem was that I hadn't done A-level physics. And you'll notice that King's does not require A-level physics for engineering, partly driven by this vendetta that I'm on about physics. Again, my head of department was in physics for a long time. So Worcester College, which is where I ended up actually doing my degree, I think trying to widen participation, you know, I'm a good bet, a state school student, working class background, first in family at university. So they invited me for interview and I fudged through the stuff about physics in there. And then they said to me at the end, well, what are you going to do? You don't have physics A-level. And I said, I'm pretty sure I can learn physics in 5 months, do the A-level, get an A and meet my offer to get into university. And I did. And when I said that to my school, they were like, oh, so you're going to drop your English and history then in order to make the time to do that? And I was like, well, I'll drop one of those. So I dropped the history, lost the Romans, but kept the English literature because I genuinely, I love English literature. I love the way that people take words, craft them, create images, and can really like transport you in what you're doing in English literature. And I'm glad I did it because I'm quite good at it. I got one of the top 5 A-level scores in the country in English literature. And I think it's kind of kept my a kind of career in a certain way. So I arrive at Worcester College. Only one of a few non-selective state school students that was at Worcester at the time. And Will, who I met on my first day, who's here, will remember that I had a very, very broad Cumbrian accent and used a lot of words which Will, and still my husband informs me, are not real words. They're words that Cumbrians use and not everybody outside of Cumbria. So I had to do a lot of work in trying to figure out where I belonged. And what I ended up doing was having my belonging in that space shaped by 3 different communities. So the friends who were in the Indie Music Society, the friends I made rowing, because I took up rowing, and the friends I made eventually starting to go to church. And I think a lot of our students are navigating this same thing, belonging to multiple tribes and communities at the same time and trying to work out how to navigate that whilst also working out what it is that they want to do with their lives. Those of you who went to Oxford will know that the course was very, very theoretical, lots of mathematical approaches to engineering, but it was general, and I did get to choose how I wanted to bring together specialisms. So I specialised in biomedical and control engineering in my 3rd and 4th year. That was the most mathsy, the control engineering was really cool. And I did a 4th year project where Renee, who was the supervisor, just said, I've got this idea that if we looked at these policies around climate change and we laid them out as if we were in a chemical reactor, could we model how you'd control those and what the feedback loops would be and all of those things to end up trying to see how we can optimize that process to achieve the policy outcome that we want. And I know now, I'm looking at Anna, that's systems thinking. We didn't call it systems thinking, we called it control. But I was modeling this like human technological system of policy measures, trying to work out how we'd get to net zero by, I think it was probably 2020 at that point, but now we're trying to do it for 2030. So I'd already started thinking, well, we've got these great engineering tools, how can we apply those to things which are not traditional engineering problems? And there are conflicting narratives about why I then stayed for a PhD. The official story is that I'd met a boy who's here and thought he was probably I was onto a good thing with him, so I should stick around and see. The other story is that I was pretty sure I could win a boat race and get into the blue boat. So having just lost a few boat races, you can pick your story. But I wanted to tell people, and especially if there are PhD students here, I had a real false start for that. I failed my transfer viva on my PhD. And it was one of those things that turned out for the best. That really annoying thing where people are saying, oh, it will be for the best. I started my first project with on computational models of the heart with a guy who actually then left to become head of department here at King's. And I would have had to have followed him to King's if I was going to carry on that PhD. So having failed that, I really rethought what is it I want to do, and I joined another group looking at mathematical modelling in the brain. So looking at how do blood vessels constrict and dilate, what governs that, how is it controlled? And nobody said to me, oh, you need to use electronic circuit theory to do that, or you need to use chemical engineering theory or control theory. It was very much, we were looking at the big toolbox that we had and thinking which things kind of fit for the things that we're trying to do. And I, despite that false start, did still manage to finish in 3 years. And it was a pretty mad last few months because we got married, I did a boat race, and I went to America and competed all within about 10 weeks of each other. But no, it was a really exciting time. But I knew that wasn't the life that I then wanted to carry on. I didn't love the brain modelling so much that, like all of the amazing academics here, I didn't want to spend the rest of my life doing that. So I loved it enough to enter a competition. I entered this IMechE PhD competition, got to the final. And the thing that they said to me after that final, one of the professors that was judging it said to me, oh, you didn't win, but they said, I suspect that you just were so good at explaining what it is that your project was that you made it sound too easy. And she's like, but you know what, if you ever want to become a lecturer, that's exactly what we need. So think, because she knew by then that I wasn't going to stay in academia, but she's like, think about that in 10 years when you're bored of industry, that you might be better off coming back to academia. So the natural step, obviously you've studied brains, is to go and look in automotive engineering. So I arrive at Jaguar Land Rover, follow my husband there, knowing literally nothing about cars. I don't know, Samjid, have you learned much about cars in your Oxford engineering degree? Learned absolutely nothing about cars or how they worked. Knew a lot about maths. So I did 3 different things when I was at Jaguar Land Rover. The first one was we were trying to start this new methodology called model-based systems engineering. We teach that to our first years now. So I was writing lots of plant models for control, quite a kind of typical control engineer job. I then got asked to join this new internal consultancy unit that was starting. So that was a really exciting time for my career, because what we were doing was researching things like this thing called machine learning. What might machine learning mean for the business, JLR? What might it do? How might we exploit it or use it for what we're doing? And I did a big piece of work looking at how do other automotive companies make cars? Like, not just, how do they design them? What software do they use? What do their buildings look like? What are their processes? How do people get better cars than we do? Because, to be honest, the cars that JLR were producing at that time were like not great, right? So we were convinced we had the right ideas. The cars were beautiful, they were fast, but they just weren't working. So we were doing that. And then I did what at the time I thought was a waste of my time, which was analysing customer satisfaction surveys. We were paying like so much money to companies to do that analysis for us, and I was pretty sure the maths was quite easy, and we could save a load of money there. I then went on maternity leave for a year, came back, and got invited to join another new team. You'll notice a pattern here. I like new things, which was called the Virtual Hub. So that was bringing together all the simulation capability in the business. And while I was there, I wasn't then working on models of bits of cars. What I was working on was models of the tests that you put a car through. So rather than my husband going to Dubai and driving over sand dunes, I was unfortunately the person for all of the engineers that loved doing that, who created a sand dune model so that we didn't have to do that. So applied fluid dynamics, modeled sand dune, so you could get pretty good fidelity and not have to fly your cars to Dubai to use their special sand. And one thing that I really identified when we were doing that is that there was a real lack of good physiological driver and passenger models. We had all these models of bits of cars that were then quite high fidelity, but not of the people that drove them, or the passengers that sat in them, or the kids that got sick in the back with motion sickness. And as a biomedical engineer, I thought, this is my niche, right? This is the thing that I can do. And actually, I got to go back to JLR later and do a fellowship and secondment in that. So what else did I do when I was at JLR? I liked talking, as you all know who know me. So I did lots and lots of outreach talks. And I got involved in the T-levels. So that was really cool. So when we were starting T-levels and degree apprenticeships, got involved in that work. And I was the industrial supervisor for a massive simulation for innovation program. But the other thing I got to do, I was well cheeky. To learn about cars, went on this thing called the Technical Immersion Scheme that Warwick Manufacturing Group ran, which taught people like me about cars. And I didn't think it was great. So I went to the director and I said, I think I can rewrite this program and make it better. I can go around all of the managers, I can find out what the latest knowledge is about cars and write a more up-to-date and modern program. And they let me. So I did it, and I made that connection with WMG. So what did I learn from being at Jaguar Land Rover? Being in a company at the time when they're trying to do that shift of innovation, so when they're trying to create the Evoque at the time, they're trying to make a car which is unlike anything they've ever done before, and realizing that the way they had to do that was by completely changing their entire organization, hiring different kinds of people, restructuring how they made decisions, restructuring their processes. And instead of you being like, I'm a tire person or I'm a steering person, structuring people around what we called attributes. So you'd be all responsible for vehicle dynamics together, or you'd be all responsible for ride comfort together. So I really saw firsthand how those structures and systems that you have in place in an organization really impact what comes out of it. And Harris just said almost exactly the same thing. I'm paraphrasing, that the liquid and the environment that you put those chemicals in really affects what the output looks like and does. So in 2015, I got wind via WMG of a job back in academia. So Warwick University were hiring 4 industrial fellows to go and rewrite their curriculum. So what they wanted was to take these 11 degree programs that they had and write a common first year and a half for those programs. So one set of modules that would satisfy all of those. So I joined some of the people to be in on that project, and was leading for systems information engineering. So that covered systems engineering, general engineering, and biomedical engineering. So having come from automotive systems engineering, PhD in biomedical engineering, I'm not sure there was anybody else who was like able to do that job like that. And whilst I was at Warwick, I was also appointed to what their equivalent of King's Academy, where you were seconded some of your time to go and do big kind of research projects in education. And it was really successful. While I was there, we increased the course numbers massively. On my course, I went 6 places up the league table and managed to get 100% in NSS for 2 years in a row, the last 2 years that I was there. And the thing that I became known for was that 40% of the cohort was female. And how did I do that? I'm just going to tell you a few things about that research. At King's, there was a piece of research maybe about 15 years ago that said that, when women are looking for jobs, they read that job description, and the words that are on that page really impact whether they decide or not to apply for that job. The words tell you something about the kind of culture and the kind of job that is. And I thought, is that the same for degree programs? Do people read a prospectus, read about how the university is selling that program and think, oh, that is a place I'll belong, or is that a place that I definitely don't want to be? So I did that work, I found similar results, and I was able to rewrite the prospectus at Warwick. But what I noticed was that there's then a disconnect, because if you're writing down, this is a collaborative way of being, we're going to have loads of connections within the curriculum, we're going to reward your kind of accountability, and then you don't do that when they get there, that's not great, and it's a cause of dissatisfaction. So I won these 2 prizes for that. Chris already mentioned those 2 prizes. And the other couple of things I did, I couldn't get away from student surveys. I still can't. My whole life is dominated by analysing student surveys. So I expanded my customer survey work to student surveys, collaborated with a guy at Strathclyde who started a spin out around this, and also did quite a bit of work with Dr. Thomas Popham on, well, how do graduates get jobs? What skills and things are they assessed on? And we found, and this is a revelation for people, graduates are not tested on their knowledge at job interviews. They're tested on how they behave, their skills and their competencies. And yet we were examining them on what they knew. So we really rethought, how can you embed competencies into what it is that you're teaching students and how you're assessing them in that. So 2020 came around, and I got this really exciting invitation and email. So I heard about King's relaunching the department, and I heard that everything they said really spoke to me. So especially this aspect of how do we equip graduates with holistic mindsets of interdisciplinarity, inquiry, and collaborative problem solving, because it seemed like pulling together everything that I was really trying to do. So why is that important, the way that we relaunched the department? I'm going to move into telling you about the last few years for the last kind of 5 or 10 minutes of this talk. So we've got really good, brilliant, in fact, for 150 years, at training engineers to produce, to make more things that may not be very good, but that's what we've got really good at. We've built entire structures and universities around that. And what we need now could not be more different from that, right? What we need now is something which is going to reverse all of that trend. We need engineers that are going to reduce carbon emissions, essentially. We're facing an absolute polar crisis. And not only that, but the students we've been used to, that we've got really comfortable teaching, their lives are so different now from what our lives were. They're facing absolute societal fracture, political unrest, and scarcity of resource. We haven't got the resources to carry on the way we're doing. And the training that we know how to do is not going to be appropriate for this. And I would go beyond that and say it's not only the training, but it's the trainers. It's us, and it's the way that we do the training. It's the environment that Harris talked about that's producing that outcome. The students themselves, we not only need to give them mastery, which we're really good at, but we also need to help them have hope that they can be change makers. We've hosted a conference this week on engineering for sustainable development, and the word hope was mentioned probably 20 times per talk, probably. So how do you give students that hope? Now, that's quite a dramatic slide. That was not what I wrote in my interview and my application. This is what I found, what I wrote for my application. I found my one-pager the other day. And what I said I would do at King's is that I would create a curriculum which covered complex challenges, would be interdisciplinary, and would have depth in the key areas that I had identified as modelling, data science, and system design processes. And we would be compassionate and responsible and have that pedagogy. So how did I do it? What have we done in the last 5 years, for those of you who sat here? Phase 1 was a phase of deconstruction. So deconstruction, dismantling, what is it that we think we know about engineering and engineering education, and can we really examine those assumptions? So I'm a design thinker, so I use how might we questions. Things like, How might we learn from other disciplines? That would be interesting, wouldn't it? Or how might we actually teach students to think outside the box? This is not going to go, so let me do that. And something that I come back to again and again, and people have heard me say this before, is something called Conway's Law. So Conway is a software engineer, systems engineer, and he says that the organisations that design systems are forever constrained to produce designs which are copies of the system that they are in, the organisational structure of that. So if you think about typical engineering faculty, and when I say faculty, I don't just mean like faculty structures and departments, but I also mean the people, faculty members. I think in engineering around the UK, we're quite fragmented, we're quite siloed. We have super strong disciplinary identities that are really hard to shake. And we have a curriculum that ends up mirroring that. We have a fragmented modular curriculum with very little synthesis. And we say that we do a research-led curriculum, but what I think we do is a research-mirrored curriculum. So our curriculum mirrors the kinds of research that we do, and the powers structures within that research, and that is not collaborative or holistic in the way we do it. I also, I'm ripping through everything, so I may as well also deconstruct our understanding of pedagogy and what it is that we're actually doing as teachers. So the thing that on the left, the triangle, is what everybody kind of gets taught when they start learning how to teach, is Bloom's taxonomy of learning. And as a design engineer, I'm saying, well, that's a waterfall model. So a waterfall model of system design is when you have to pass through each stage before you're allowed to get to the next stage. So you get your design reviewed, and then you're allowed to go to the next bit. And so we end up with our curriculum where full of understanding and remembering. Students get really good at remembering facts, understanding and applying kind of mathematical procedures to questions, following the recipe in labs, and they get very little time at the top of that triangle. They get very little time to create. And it's almost gatekeeping in the way that we do it. And in 2020, when I joined here, there was this book that I read called Hope Pedagogy. And it said that if you spend all your time in analysis and evaluation without the opportunity to see how to get out of it, how to create solutions, then you don't have hope. That's how you lose hope. So obviously the challenge to me was, how do we bring creativity into the heart of the curriculum, the create first pedagogy? And also, how do we develop these kind of agile and iterative learning cycles, which is how I see people doing design in industry. So I developed this vision around the word make. There were three ways of using the word make. So the first thing I thought we should do is teach students how to make things better. So things that work better, things that don't break, things that are more inclusive, things that are more sustainable, more functional. The next thing is I wanted to teach us how to better make things. So not only looking at the outputs, but better materials, better manufacturing processes, better design processes. And by doing that, I thought we could probably make things better. So we could have impact on global challenges. And we established this vision. We had lots of kind of lovely industry people come and kind of join us in it. And this really struck a chord with us when we were talking about it. And design, for me, was the key to those better engineers. So design, I'm not going to go through this slide, but these are the design skills that are kind of acknowledged. Design is discipline agnostic, it's not even engineering. Design is like business and healthcare, it's used everywhere. And the one that I really love in this, navigate ambiguity, that's really important for designers, and I think that's really important for change makers, and the ability to learn from feedback. Our students are terrified of failure. Our students, because they're terrified of failure, are also terrified of feedback. And more so than we ever were. And we've got to really try and help students to understand that feedback is a positive thing. It helps you improve and it helps you get better. We had to build a team. If Professor Sholok was here, she would tell you all about how we did that. But I wanted to kind of highlight a few things. We had open education committees. For 5 years, anybody could vote in those committees and kind of take part and say what was happening. We recruited our education-focused academics not around module gaps, but around skills. So each of them is associated with a particular skill that we need in the curriculum. And we recruited our technicians as graduates of Russell Group universities to really disrupt the traditional hierarchy of where technicians sit in engineering departments in the UK. And they've been an absolute key part of this student experience, as have the students. So phase 4, and we'll be quickly kind of coming towards the end. Again, as a design engineer, there's something that you learn is that you have two kinds of requirements that you set for things that you design. You have what we call the functional requirements, that's everything it should be able to do. And then you have these non-functional requirements. They describe how it will behave. That's the systems engineering methodology. How should this thing behave in different scenarios? And we thought the same thing for our students. We can pretty solidly tell you what they should be able to do by the end of each year. But we hadn't really thought about, well, how should they behave? Having come through our system, how do we want our students to behave? So we defined these at different years. We said, they should be self-aware, culturally competent design thinkers. By the time they get through third years, they should be socially responsible technology innovators. That would be their way of being, that would be their way of behaving. And to do that, we created this curriculum of design cultures. It's where we have every semester starts with the need to create, the impetus to create something. You go through your evaluation analysis phase, analysing data, analysing experiments, and hopefully through your lessons learned process at the end, you're applying and remembering the things that you're doing. And beyond that, we also recognise that in engineering, there is not just one way that a company works. And typically in a university, you'll learn one way of doing design, but we, over 4 modules in the first 2 years, create 4 different design cultures. So the first semester with me, it's like working in a startup. We have loads of post-it notes, loads of whiteboards, loads of kind of storyboarding and things, lots of pitching. They move through this kind of systems engineering culture, all the way through to an entrepreneurship culture. So how do innovative and entrepreneurial B Corp type companies work? Way has designed that module for us. And how can we then say to students, well, if you really thrived in one of these modules, maybe look for jobs in those kind of cultures and sectors. We're trying to replicate the options that students have when they graduate from here. So I could tell you about our environment for a long time, but something to just kind of pick up on that is that obviously drew on my JLR work when we were looking at how people made cars, how their buildings worked. And it's also inspired by what Google call activity-based working. So Google do a lot to try and move people into a particular space for a particular piece of work that they're doing. So if you are needing to prototype, you'll go into a specific space for prototyping. But those spaces are kind of naturally built into the workflow of their day. And what we didn't want was a building where the makerspace was over in one bit, the labs were over somewhere else, that we see in a lot of universities where everything's really distributed. We wanted to have this all together so that students could, in an agile and iterative way, move through all of these different places. So I've done, I've moved into thinking not just about the system that we have here at King's, but about the wider system. So Alistair's here, he was the chair of this QA subject benchmark statement. He let me add values to that statement for, I think, the first subject benchmark statement that had values in it. As part of the accreditation committee, that's a system that lots of people who work in engineering education blame for the lack of ability to innovate, but really working on that system to help people innovate. So what are my lessons learned? I think I started out 5 years ago as a systems thinker. I knew a lot about how systems behaved. I knew a lot about how to analyse systems. And in the last 5 years, I would now call myself a system shaper. Is that a real thing, Anna? So a system shaper, I would say, moves beyond systems thinking into working on the systems that land us where we are, overcoming the inertia to change that these systems have. And the 2 things that I've really learned from that, I've had to really widen my lens, even more than being the generalist I was, to go outside of engineering and really look. And that's what King's is great for. We don't have a building which is the physics building and a building which is the maths building. In our faculty, I sit on an education committee with physics and maths and chemistry. So I get to see how other disciplines work. And to solve the problem of engineering education, I think we need to have the same approach. And I also have learned that engineering skills deserve just as much research, maybe not from the funder's perspective, as engineering knowledge. So my amazing PhD student is here who's working on engineering skills. And also looking back, everything's always connected. I think people say, did you have a strategy for this? I didn't have a strategy for this, but it all makes sense when you look at it back together, right? All the way back to that work at JLR, some of the things I thought were a waste of my time that I've reused again and again. So if you're a student sat here, nothing you do is ever wasted. You can always come back to it. So what's my manifesto? I'm sorry, I'm run over as well. I would love an engineering curriculum that equips students to shape the future, to create the future, not just to survive it. And we do that by moving from that evaluation analysis, which we're obsessed with as engineers, into creativity and hope. I think that choosing engineering should not mean choosing to leave your entire family and community and culture behind and move to a city so that you can do that job. I think that we should have engineering opportunities not only for people to come as they are, but for people to come where they are. I don't know how we do that, but that is what I would hope for the future. And that systems shape outcomes. If we're really serious about changing engineering education, we have to also be serious about changing educational structures, academic structures, even the way we work in departments and faculties. So some gratitude, because it's an inaugural lecture, you've got to finish with some gratitude. I've had more sponsorship and opportunity from amazing people than you could imagine. So from my supervisor, Stephen Payne, who had never had a student with a 2-1 before, and was like, I'm not sure you're capable of doing a PhD, but I'll take you anyway. Through Joe Lopes, who put me up for all of these outreach activities. Aram, who asked me to join his internal consulting unit, actually was a visiting professor here at King's for a while. Spencer, Elizabeth Donnelly, who gave me 2 different prizes in 1 year and really loved my story. And then Barbara, of course, who I really wish could have been here, but Barbara, who gave me this opportunity of a lifetime to design a department around the kind of education that we wanted. And then to my husband, who's here, many of you know that I love to sing because you were at the Christmas party. So when we first met, he was my sound man. And the job of the sound man is to be behind the scenes, solving all of the technical issues before you get to know about them, making sure everything goes smoothly, and then making you sound good and twiddling the knobs to make you sound even better. And everybody should marry their sound man, absolutely, because that is what he does in life as well. He's a really super successful person in his own right at JLR, and I'm sure he'd love a wife with a normal job. But he doesn't have that, so he does everything. He does all of the pickups and the drop-offs, cooking, sorting things out, loading the dishwasher that I'm not allowed to do. So my life wouldn't be the same without him. So thank you, everybody, for listening and allowing me to speak longer than my allotted time. And I'm grateful for you all. Thank you.
Well, thanks a lot, Claire, for that. That's great, a great talk, and I think there's a lot to take away from it. I think one thing that's great is that, Claire's better than at a lot of things than me, but clearly she's much better at physics, because it took me, I don't know how many years I was in that department, but I still don't know physics, and she mastered it in 5 months or something, so that's amazing. Also, I think you achieved more in your PhD than I did in about 30 years. You went to America, you won a boat race, which I've never won, all these things. That's quite impressive. And also, I think you're ahead of the game with brains to cars, because I was talking to the leader of McLaren Applied, and they said that people are now buying Formula One cars just to train machine learning models because they're the most complex things ever. So I think it's not, you're just ahead of the time, I think. And obviously I was talking about impact when I was talking about Harris, and Claire has had such a huge impact on the department. As you see here, that not only does it have her fingerprint, I think it has her whole, I don't know, 2 hands printed or something. It's massive impact. And for me, she was talking about what a sound man does and all the support that her husband gives her, but she does all these same things for me, and making things as easy as possible in my first year as head of department. So I really appreciate that. And I think that, she's done fantastic. And also she's an amazing mentor to everyone in our department as they go through the Fellowship of Higher Education and in general, and has done so much alongside Harris in establishing the environment that we have in the department that is, second to none. So thanks for all of that, Claire, and thanks for a fantastic talk tonight.
Well, for those of you who don't know, I'm the Dean of the faculty here, and apologies for being a little bit late, but I was very glad to get most of Harris's talk and all of Claire's talk. So for me, this is a real highlight of one of my job, coming to the inaugural lectures, because our professors are so important in terms of the leadership that they bring to the departments, to our academic colleagues, to our students. You know, you are our leaders, you are the people who are setting the tone, setting the culture, providing an example, and having the two of you as leaders and deputy heads is a fantastic thing for our engineering department. I have to say the reason I was late today was because I have spent all day in promotions panels for professors and readers, and it's all highly confidential, but I'm feeling happy, so that's good. Just a few comments, because I'm sure you're all desperate to get to the drinks and socialising, but I did want to reflect a few things that I heard today. Incredible research and impact from Harris's work, and what really strikes me is this interdisciplinary aspect of the work. So it's not just engineers doing their own thing, it's engineers working in a really deep way with clinical experts, with our medical colleagues and so forth. I think this is something that's really important and something that's very central in King's about how we do interdisciplinary science and engineering. I also love the fact that we have this integration between our computational expertise and work there and actually the experimental side, and then of course translating it to have impact and working out what's going to happen, not just in King's, but around the whole world. And this aspect of making the world a better place, and specifically engineering for a better world, I think is crucial and something that's very, very strong in King's. Moving over to Claire, there's so much there which really chimed with me. I'm glad you mentioned the Battle of the Bands. I think if I was to say two things which were real highlights for me at King's, one was my very first introduction to King's, which was Charlotte in the technician showing me around the makerspace when I came for a visit, which just amazed me, getting to see the quad and the makerspace. And the second highlight was our Battle of the Bands for the Christmas party, and seeing the engineering band where Claire lead vocals. Now I'm trying to think, who was the rest of the team? Who else is here from the engineering band? The engineering was the band that formed for the event, wasn't it? So we had... anyway, it was a highlight. It was amazing. More seriously, though, Claire, I think some of the things you said really chimed about what's so important about you've brought to the department and how you've been a systems shaper. You have shaped what the department does, how it is doing its education, inspired that real change of thinking. And I think this idea of hope as being an absolutely central thing that we should be inspiring in our students, in our academics, in these times of a lot of uncertainty and a lot of challenge. We need to embed that creativity, that collaboration, in order for our students to thrive and our staff to thrive, and to really go out and engineer for a better world. So that was really inspiring to hear that articulated so clearly. I also really recognise this aspect of navigating ambiguity. As we train our engineers and tackle those, I think you call it the wicked problems, this is in the engineering space, but it's also in our wider space. As we face challenges and uncertainties and changes in how we do things and how universities operate and elsewhere, we have to continually be agile and be willing to listen to different ways of doing things and different approaches and navigate that ambiguity, because there's not always a simple solution for those wicked problems. So I've been absolutely delighted to be able to be here and listen this evening. So thank you so much again, Harris and Claire, and to all of you who've come. It's an amazing Department of Engineering we have, and engineering at King's is really something that we can all be incredibly proud of. So thank you.